Okay, so good morning, everybody. Welcome to ONOS TST steering, so I guess redundant TST meeting. Today, this is a public and recorded meeting, and today we're going to provide an update on the latest µONOS effort, specifically on a performance milestone kind of a sprint that we were working on for the last month or so. And it's a number of people will provide the update. So first, let's, so clearly the update will be the top of the agenda, but as part of the sprint, we've done also other type of work. For example, Shad worked on the Southbound interface proposal labeled as E2. We also provided overall Helm chart for the overall solution deployment. Obviously, there's a phone call.
191.
1 second. Let me get rid of this stuff. Carol, okay. Sorry about that. It's a problem having a separate home line. We also did some work on test framework, which was formerly on it, and Jordan will talk more about that. Also, Ray worked on a RetryClientinterceptor mechanism, and then we finally put together a set of initial release tools and cut an initial 050 release. So, but clearly the dominant part of the agenda will be the performance update. So the objectives of the performance milestone sprint were we wanted to validate that the currently proposed architecture can meet the stringent requirements for real-time and near real-time operations. And specifically, we're interested in making sure that we can tighten up the P99 latency for things like handovers. And as part of that effort, we wanted to identify and eliminate any architectural bottlenecks that may exist. Also further optimize the flow of information to reduce the latency. And Jordan and Sean will talk more about that. And we wanted to validate our results by running an empirical test at reasonable scale. Now, granted, this is not a full production scale, but it's still a reasonable scale to be able to test whether a single node can deal with a reasonable size load. And so we targeted 10,000 user handsets and 100 base stations, and to be able to run at least at 100 handovers per second. In reality, we actually ran almost triple that, but more about that later. So Jordan, can I let you take this from here?
Yep. Yeah. So so when we started taking a look at handover latency, some of the first issues that we encountered were just that the initial benchmark showed some of the issues with how we had initially implemented the stores. So we sort of like migrated some of the code over from ONOS config, and in ONOS config we had been using consensus, but consensus was never suited to a low latency application like we need for handovers, and so we needed to find a low latency solution for the stores. Next slide. So the first thing we did was replace the consensus service that was backing the stores with a low latency cache. The good thing is that Atomics, a lot of the work that we did last year on Atomics for µONOS makes this really simple. We're at the point now where we can just change the image that we deploy in Kubernetes, and you can change the protocol and change how data is stored. And so when we did that, when I benchmark the caching, the distributed cache backend, I get latencies of less than 1 millisecond, like worst case around 1 millisecond. But when we deployed that inside as part of the handover app and measured the handovers, we still saw latencies that were much higher than that. Part of the problem is that we're doing a bunch of writes inside of ONOS RIC that are serialized, and that can add up But there seemed to be some other issue that was also going on. And so it didn't totally solve the problem. So we started experimenting with asynchronous writes to solve the latency issues that we were seeing. And that's where we came to starting to work on asynchronous stores. Yeah, so the idea of the asynchronous stores would be that we modify the stores to return immediately on writes and propagate updates to the distributed cache in the background. Use data locality to ensure that writes and reads to the stores are always very fast and always local, and then use distributed systems techniques to still preserve consistency across nodes in H8 deployments. And so this is what it looks like. Next slide. So taking the telemetry store as an example, when we write to the telemetry store, next slide, you'll see what happens. So the telemetry store immediately writes an update into a local cache and then puts it in a queue to be propagated asynchronously. And so what that allows is for the data becomes immediately accessible for reading the write returns, and so we can continue propagating that down to applications, to the handover application. Yeah, and then in the background, it's propagated up to the distributed cache, and then from the distributed cache, it can be propagated to other nodes, which they can then just put them in their local cache. Yeah, and so this is, yeah, go ahead, next slide. Yeah, and so the way that we preserve consistency while doing this is using some of the techniques that we used in the original ONOS. So writes to the stores are assigned a logical timestamp, which we can use to determine order when the order of updates when we're propagating them around the cluster. Writes are propagated to the distributed cache if they're newer than any update that was propagated from a different node. Updates are propagated through the distributed cache to other nodes, and then those nodes cache them locally if they're newer than the updates that are in their local cache. Reads when switching nodes if there are failures, and a client has to switch nodes due to a failure. The reads wait for updates to be propagated so that they never see data in the stores go back in time. And then those timestamps can be propagated through southbound and northbound APIs to provide consistency for clients. And then the other component of the store design is that they promote scalability. So the messages that are coming from the southbound that go into stores are partitioned among the nodes in multi-node deployments, and that's done by we added a partitioned mastership election, which we use to determine node affinity. Basically, keys are computed for messages that arrive from the southbound, and those keys are mapped to a mastership election, and that is the node on which the cache is most up to date. And so by performing writes and reads on that node, they're almost always local, and that improves the latency, as we'll see. And then mastership elections. So mastership elections are still backed by consensus, even though a lot of the stores are just stored in a cache, because the consensus protocol still gives us consistency, which is what allows us to determine order for the cache. And so this is what it looks like. Previously, we just had one backend that we stored data in for ONOS RIC. Now we have two. There's a consensus backend and a cache backend. The consensus backend is used by the mastership store. The telemetry store uses mastership to determine data locality and then stores its data in the cache. And I think that's all I have. Yeah, so yeah, you can go to the next page. So there are some improvements that this is just an initial implementation that we have right now. I think we need to make changes to like some of the concepts that are implemented for the stores need to be sort of propagated out to like the Southbound API. Southbound API can take advantage of mastership to implement data locality and improve performance in multi-node deployments. But that's probably the next task on my to-do list. So I think Sean has some stuff to talk about also.
Yeah, so thanks, Jordan. That really was a big help to the performance. So while that, you know, a problem of the stores with consistency was in place, they were actually masking some other problems as well. So we just disabled them temporarily to see what the other problems were. And one of them we found was the handover app called the ONOS RIC to make a handover, and it was a synchronous request response over gRPC. And the setup cost of that was actually costing us milliseconds. You know, so it basically was just, you know, had to establish the HTTPS context, the TLS context every time. And so what we did is made it a streamed connection. So basically streaming from the client to the server basically meant that you set up the connection once, and basically as handovers needed to be done, you just sent a message across. Previously as well, the handover app itself was trying to build up a state of previous handovers to see if a handover request was a duplicate. And basically we found that that wasn't necessary at all. With that situation, we couldn't get above 300 UEs, you know, and now the situation we're in, we're at 10,000 UEs. And another thing that helped the performance is that on the southbound of the ONOS RIC, where it contacts the RAN simulator, the RAN simulator is actually offering a gRPC server per cell tower. So, you know, when we have 100 cell towers, there's 100 gRPC connections going on. Now that's just a simulator, but it's there to represent the control plane centralized unit in the future situation where there will be many of these things in the field. So it's I suppose it's got a performance benefit, and rather than pushing everything over the one link, but also it's more realistic because it's an indication of where we're going in future. I have a link to the sequence diagram. Yeah, maybe just see if it'll come up. Yeah, so it's pretty big. This
can you see it?
Yeah, I can see it for sure. Yeah. So basically, yeah. So maybe just go to the top, to the green section. I think is the RAN simulator.
Sorry about that. It's moving on me too much.
Oh yeah, there we go. So the blue section is, I mean, people can view it offline if they want afterwards, just to give a guide to it. The blue section is the ONOS RIC itself, and then I can't remember what color the section on the right is, pink or something, or yellow, is the handover app. And so the message goes from the ONOS, or from the RAN simulator across. So we're talking about the purple section here. So it goes from the RAN simulator across through the ONOS RIC to the handover app. Handover app makes a decision, sends the response back, and there in that section where it says open gRPC connection, open gRPC session, yeah, down one, and basically that's basically now just put the message on a stream, and so it expedites that message back across through the ONOS RIC. And then as you can see, there's like a connection per tower. So when you're doing a handover, you'd receive the handover information from one tower on one gRPC channel, and now you're sending it back on a different gRPC channel. So there's, I don't know, if people want to view it offline, it gives a lot of the detail. There's no point probably going into it in too much detail. I haven't updated it for Jordan's new stores, but I will update it and put in the cache as well, and show how the mastership relates to each other. You can go on to the next slide on this one, Thomas.
Did it come up?
This is one I captured earlier. So basically this is the map view of the RAN simulator, and basically it's simulating 10,000 UEs on 100 cell towers. And the fact that, you know, each of the cars are colored according to the color of their tower. And so basically what this is showing is that the handover app is working properly, that as cars drift off into the realm of other towers, a handover event happens, and so the color of the car changes. And basically this little patchwork quilt is showing that the handover is working and keeping up with the demand in real time.
And it also shows the load balancing application working as well too, which kind of adjusts the density per square.
Yeah, so basically the load balancer is adjusting the diameter of the circles around each tower. I think in this particular image, it might not have been present. And I know Wuzhong is optimizing it. So for this particular screenshot, all the towers have the same size circle, but it's I think it needs some optimization to deal with 10,000. But yeah, it's a very worthwhile addition to it. I think that's all for me, Thomas.
That sounds good. So, Wuzhong, do you want to take it from here? Because this will be the kind of the performance results section, or do you want me to cover it? How do you want to do that? I think Wuzhong's muted. So let me at least cover the performance test setup here, and maybe he can go over the numbers themselves. So first of all, this is a single node controller. So we basically run just one instance of the controller itself, with one instance of a handover application and one instance of the load balancing application. As Sean mentioned, we were running against the RAN simulator, to which we were establishing one connection per base station. In this case, it would be 100 base stations. The handover application is a very simplistic handover application, which just triggers a handover based on instantaneous value of the quality of the signal for the handset. And the load balancing application is something that takes a look at the global load of each of the stations and adjusts the RF power of each station to be able to sort of shed or accept more UEs into its realm, kind of through a feedback mechanism, to be able to indirectly control the quality of signal that the handover application will then end up actually taking action of moving UEs from one place to another. This is using the E2, the first generation E2 gRPC Southbound interface, and the first generation of the C1 near real-time interface for northbound, on the northbound of the controller. And what we were trying to do through this experiment was basically to see if you can achieve P99 latency under 9 milliseconds for the whole, for both of the hops, including for the stores involved in storing the information and retrieving the information. So the tests were, Wuzhong, are you on? Do you want to go through these things? I just want to give you an opportunity.
Oh, yeah. Oh, sorry, I was muted. Yeah.
No, no worries, no worries.
So this page you already made before. Anyway, so with the test in the test, so we use the ON.Lab C220G5 node in Wisconsin cluster, which has 20 cores, Skylake 2.20 gigahertz CPU and 192 gigabytes RAM. And also I conducted this test for 3 minutes, which make 50,000 handover events. And also I used 3 different CNIs, Flannel, Calico, and Kuberite router. And also there are 4 options. First option is that the ONOS rig bypass the atomic store, and also handover application itself is in the ONOS rig, not a different container. That is the option 1. Option 2 is also bypassing the store, but ONOS rig handover application is running on the different Kubernetes pod. Option 3, we are using generation 1 atomic store. Option 4 is using asynchronous atomic store. That is the environment. Could you go to the next slide? Yeah. Here's the summarized result. Most likely, Flannel CNI has the best results. And the option 4, average latency was 832 microsecond, and P99 latency was 4.6 millisecond. And P95 and P90 latency was 1.9, 1.3 millisecond. And for the reference, option 1 and option 2 shows that the average latency was 250 microsecond, whereas P99 latency was sub 1 millisecond. So yeah, that is the summarized results. And in here, I summarized the other results with the other CNIs like Calico, Kubernetes. So as you can see here that Flannel has not always, but Flannel is most likely better performance rather than Calico and Kubernetes. So we can think that for the SD-RAN with the best performance, we should use the Flannel CNI. Yeah, I think, yeah, that's all. Yeah.
That's great. Thank you. Thanks for running it. And also just to point out, the option 4 is kind of what we assume to be the most realistic scenario, clearly because we clearly want to be able to store the information, retrieve the information, be able to hand it over in case of failures. And also it verifies that our 3-tier architecture is going to be able to meet those results. So the other options were really primarily provided just so that we could see and we could kind of definitely prove what the cost of each of the hops was and what the cost of the different implementations of the storage was as well. So thank you. So yeah, so the key points and kind of some of the caveats of the performance experiments are as follows. So we validated that 3-tier architecture can indeed meet the requirements with reasonable headroom allowed for the latency. And also this means that in production deployments, when we do need to have, because it's unlikely that in real production environments, the equipment itself will support gRPC, which means that we will have to insert a gRPC to a SCTP proxy. But even if with that proxy included, we can expect at most additional millisecond additional latency for the full round trip, which means we're still comfortably below the 9 millisecond latency. Also, one of the lessons learned from this was that C1 APIs should exclusively use the streaming for latency sensitive calls. As Sean pointed out, because there's a lower cost of setup, plus also And the asynchronous streaming will also result in better scalability for applications because the non-blocking, because if you have blocking request response call, you're effectively kind of blocking a thread, waiting for the response to come back. With asynchronous processing, you most likely just going to fire your message and move on to other things, and then have a event handling loop deal on some sort of a shared thread with the response. And so the applications should be more robust and better performing, and also scale better with respect to thread resource utilization. One caveat here that needs to be explicitly pointed out is that the handover application that we use is very trivial. Like I said, it uses instantaneous value of the CQI to be able to trigger a handover. Clearly, the production or real handover application will also need to probably consult some historical data sources in order to make intelligent decisions. Now, having said that, the applications themselves will also need to be heavily optimized in that it will include any data sources that they use to consult for their decisions, which means that they will not just be able to willy-nilly be able to access slow databases out in the wild, but they will probably also have to take steps to make sure that their data sources are either reasonably cached or reasonably pre-cooked or optimized for speedy and predictable access times. But that's work clearly that will be, we will try to encourage through the C1 API, and also through kind of spelling out very clearly what the contract for the applications will be. But I think with the results that we've shown, if you just even consider P99 latency, basically we've consumed less than half the budget, which means the 50% of the budget will still remain for the applications to operate in. And that's for the P99 latency. For the mean latency, actually, the results are much better than that. Okay, so as part of the sprint, we've done also other work. Shad, who's unfortunately not here, has worked on proposing the kind of next version of the E2 model, and I think we'll probably have to wait for another update to hear the details of this, because this work is still flux anyway. But it has to basically do with proposing something which is more amenable to the operators, to the ORAN spec. But I will let Shad talk about this next time. Who wants to provide an update on the Helm chart? Is that would it be Jordan or Ray? Who wants to do this?
Bujang?
Yes,
okay.
I updated, yeah. So we have an umbrella chart called SD-RAN. By deploying a single this umbrella chart, we can deploy multiple charts simultaneously. So it has a multiple subchart for ONOS rig, to applications, simulator, GUI, topo, config, CLI, and then monitoring, which includes the Prometheus and Grafana for dashboard. So the way how to deploy this umbrella Helm chart is updated on the µONOS documentation website, so you can check. And among the subcharts, there is a dependency between ONOS rig and two applications. Well, to resolve it, I added a dependency checker on those Helm charts, and with this application, so we'll wait until ONOS rig is in the ready state when deploying this umbrella Helm chart. However, the dependency itself has to be removed in order to make much more cloud native SD-RAN. Maybe next release I will remove it. Also, we'll do a code refactoring here since code quality is not really good, so I will do it. Yeah.
So while we're on this topic, there are a couple other changes that were made to Helm charts also. So I added, so previously we were using like environment variables to do some configuration stuff. We updated ONOS libgo to add like a configuration abstraction, and then added configuration files to the Helm chart. So each of the services have use a config map to store a configuration which is derived from the Helm chart values, so you can override them on the command line. And then each service can define its own custom configuration format in a struct in Go. So it's should be easier to add non-trivial configuration options. And one of the the initial configuration options for every service are there's a configuration for configuring the atomic store backends, and you can also configure the logging now in Helm chart values. So.
That's great. Thank you. All right, Jordan, do you want to talk about Helmit?
Yeah, so I've talked about ON.It, the test framework that we were using before. Since we're using Helm charts a lot more, I modified ON.It to support deploying Helm charts, and we ended up renaming the project and making it sort of decoupling it from µONOS. And so there's a new project, Helmit, which is just an evolved version of ON.It. So it provides an API. You can go look at the repository. So there's tons of documentation in the repository. It's finished now, but basically it has an API for deploying Helm charts and doing integration tests, benchmarking of Helm charts. And so we started, so that's been released, and we started updating all the tests. So we added tests using Helmit to the charts repository. So it can, so in the charts repository, it sets up the Helm charts and verifies the resources that they deployed. And we updated the ONOS RIC tests and benchmarks to use the Helm charts. And so there's some stuff that's still a work in progress. Like we're still moving the ONOS config tests over to it, but we've made a lot of progress there.
Yeah, and also has an added benefit is that some of the test containers don't have to be generated for the individual projects, right? Because they're generated on the fly from.
Yeah, one of the painful things was every time you made a change, if you were working on tests, every time you made a change to a test, you had to build. In ON.It, you had to build an image, push it somewhere, whether it's a kind or to another cluster. One of the problems that I solved when I was working on Helmit was just not having to do the Docker image thing. So it has just a base image, and when you give it a test to run, it dynamically compiles the test and pushes it to a Docker container running inside Kubernetes and to run the test. And so actually, even though it's basically the same thing, you're still building the code and pushing it somewhere. It turns out to save tons of time. So I'm extremely satisfied with it.
Yeah, a lot of disk churn too, right? Because you don't have to be laying those images down and everything else. So that's great. Okay, Ray, do you want to talk about the Retry Interceptor?
Sure. Jordan had implemented a Retry Interceptor for gRPC connections in Atomics. And we had a bunch of places in ONOS where we were basically, we had to put dependencies in between the components so that if one component required another, it would come up and it would fail if the connection wasn't there. So the idea behind the Retry Interceptors is twofold. One is to solve that problem. So now, if it comes up and say you have, Rick wants to talk to Topo, Topo's not up yet, Rick will just have an interceptor in there that will retry the connection until Topo's there. We don't need to do these hardwired Helm chart connections anymore to make that happen. The other thing it does is down the road when we start having failover and HA scenarios, we really have to have all the channels protected against some kind of handover happening at the Kubernetes level. So what I did was I took the code from Atomics, I put it into the ONOS realm, and then found most of the spots where we're actually doing gRPC connections and made them use retries. Sean backed me up a little bit and fixed a few of them that I had used the singleton model instead of the stream model. But this should make the Helm charts a lot simpler now because we don't have to have these dependencies anymore.
That's great. Okay, and then let me talk a little bit about the release and publish. So we intended to, back in January, to run an initial release of ONOS config, but we got a little bit bogged down and switched very quickly to working on SD-RAN. So we pushed the kind of the release process off a little bit, but finally became clear that dealing with hash codes for inversions as for managing dependencies and dealing with kind of anonymous Docker containers was really no longer sustainable. So a few days ago, we finally bit the bullet and put some at least preliminary work to be able to publish well-known versions. And so there was a new tool created called publish version that basically allows us to tag the repository and push the tag upstream to GitHub, and also to be able to build, tag, and publish corresponding images to Docker Hub if a repo has Docker images. We also integrated that tool to various make files so that you can just basically publish by running a make publish target. As part of this also, we standardize on a version format. So we're kind of following the Kubernetes convention where the version is prefixed with a lowercase v. You use a 3-segment numeric version for semantic versioning. And we allow an optional dash separated extra modifier, so we can tag things like alpha or beta or RC releases. We use this to publish the initial releases for these various repos. We use 050 as our initial release. And also Sean had created, but this takes care of only of the act of tagging and pushing upstream the images, but it does not really handle revisioning the dependencies. That still has to be done manually. So to help with that, Sean put together a tool to bump the dependencies for each project. And we will now next work on integrating that and figuring out how to best, integrate it into overall scheme of things so that we can version whatever scope of components we want to version. Because the whole idea with µONOS is to follow the what was done in CBA and Cord and other projects, which is not to version everything at once, but to version individual components and let them evolve in their own time frame. But of course, if you version a component that's depending on where it is in a dependency graph, that may cascade out. And so we want to come up with a mechanism that will capture properly the dependencies, but also allow us the sufficient control to version only the things that we want to version. And so there's definitely much more work to be done here, but at least we've taken a step to have the initial base layer of tools and of the actual release cut. I think that's it for the work done as part of this this release. But again, the key part here is this bit right here. Are there any questions or additions that people want to raise? If not, I think we can probably conclude the meeting. I was hoping that either Guru or Oz would be able to attend, but since they didn't make it, we can maybe give them a pointer to the recording or give them a, just a summarized version of this in a separate meeting. So I think that's it for today. I think next week we will hold the deferred milestone for the 2.4 release of ONOS Classic. Right now, that don't, right now I still have to figure out what will be presented, what will be on the agenda for that, because most of us have been working on micro ONOS rather than ONOS Classic. But right now it's scheduled for next week, and so stay tuned to that. Otherwise, we can probably call this a day, and we'll see each other next time. Bye-bye.
Bye.
Bye.